Alright, so here you're asked to discuss the continuity of these functions. Now, when you go through your homework, you're not actually going to have the graph already there. Well, you do on some problems. You already have the graph, but then some of them you don't. Of course, you've got your graphing calculator that you can use to help you out. But you also just need to be aware of when it's this type of function that I need to be careful about so-and-so. Or if it's this type of function, then I need to make sure that I check for whatever. So you just kind of have to be aware of what kind of function you're dealing with. The first one that you have here, and even the second one that we're going to do, would be considered a rational function. Of course, if you remember, rational means you're always dealing with a fraction. When you're always dealing with a fraction, you always have to make sure that you do not have 0 in your denominator. So even if I didn't already have this graph put up here, immediately you should think, okay, now I'm going to have to be careful about what happens in my denominator. I can never have 0 in my denominator. So obviously, if you let x equal 0, that would give you 1 divided by 0, and that's undefined. So that would tell you right there has to be some type of discontinuity, okay? Now, of course, you've got the graph here already, and if you go to x equals 0, of course, x equals 0 is also your y-axis, but if you notice, like the right-hand side of 0, your graph turns and goes up forever. Of course, they only show you just a little portion of it, but it makes the same little shape here as what you see here. As it approaches 0 on this side, it's going to turn and go down forever. You actually have a vertical asymptote. Of course, they don't have it dotted in because it's right on your y-axis, but there is a vertical asymptote at x equals 0. So one of the first things we talked about was the difference in what they call a hole, a jump, a gap, and having a vertical asymptote makes what they refer to as a gap in your graph. So that would have to be a discontinuity. Okay, so when it says discuss it, like this is what it would want you to write down as your answer. Just say that there's a discontinuity at x equals 0. And you would need to go ahead and specify whether it's removable or non-removable. So I can't just simply fill in a hole and fix this problem. So remember, that means that it would be non-removable. Okay, so that's all it's looking for when it says to discuss continuity. So again, you've got to be aware of what type of function you have and not necessarily always rely on your graph all the time, but you've got your graph there that you can look at in your calculator to see what's going on. All right, the next one, as I told you, we're going to look at the first two were both rational functions. So again, I've got the fraction, and I definitely have to be careful about causing my denominator to equal 0. So the only value that would cause my denominator to equal 0 would be x equal 1. Now, I know that right there tells me that I have, for sure, a discontinuity at x equal 1. Now, you have to know what's happening there, though. Like, what is that going to make the graph do in order to know whether it's removable or non-removable? Well, a while ago it was a vertical asymptote. Of course, you've got the graph here already looking at it. Of course, if you graphed it in your own calculator, you go to x equal 1, even in your calculator, it's not going to show that you have a vertical asymptote. Now, the fallback to your calculator is, remember, it doesn't show you the whole. Now, like I said, if it's a vertical asymptote, you'll be able to tell that on your calculator. But if you know it's not a vertical asymptote, but you have some discontinuity at x equal 1, it should be a whole. But if you want to just verify it, first of all, you could look in your table, and if you go to x equal 1 in your table, remember it's going to show you an error. That just kind of verifies, yeah, there's something going on at x equal 1. But the other thing is, if you actually plug 1 in, of course we already know it makes the bottom equal 0, But if it also makes the top equal 0, you get 0 on top and bottom, that's actually going to let you know that it is a hole in the graph and not a vertical asymptote. Like, see back up here, if I substitute 0 in, I don't get 0 over 0, I get 1 over 0. So as long as you don't get 0 on top and bottom both, then it is a vertical asymptote. But if you do get 0 on top and bottom both, then it is just a hole. Well, when it's just a hole in the graph, remember, I could come in and color that in, and if I colored in that hole, then I wouldn't have that discontinuity there anymore, so this is removable. Okay, next one. Now this is a piecewise function, which piecewise functions are a little bit harder to deal with in your calculator. Because if you're going to put this in your calculator, what you'd have to do is actually just put this in y1, put this in y2, and then just look at this one, you know, when you're less than 0, look at this one when you're greater than 0. The thing about piecewise functions that you have to make sure of is, do they connect up to each other? Now, you had some graphs that I had up here a while ago, and let me just throw this back up here. Like, I had given you these pictures earlier. Like, this was what they called a jump. This is actually a piecewise function that's just where the pieces don't connect up. So that's what you've got to figure out. Do they not connect up like this? Of course, you've already got the graph of this one. I've already put it on here. This one connects up. That's what you've got to figure out. Because if they connect, it's going to be continuous. Okay? If it doesn't connect, then it's not going to be continuous. Now, the place that you always have to check to see if it's continuous or not is always going to be that number right there. That's going to let you know where you've got to check, okay? Of course, you can tell by looking right here. See, that's actually where they do connect up. But here's what you would do. Just take the 0 and plug it into the first piece. So I'd say f of 0 equals, and then I have 0 plus 1, which is 1. Okay, do the same thing here. Plug this one in to this second piece. So then I would have 0 squared plus 1, which is 1. Now, the fact that these two things come out to be equal to each other, now remember, these two numbers that you have here are y values. Okay, so actually what you have is, on this piece, you have the ordered pair 0, 1. But then on this piece, you also have the ordered pair 0, 1. And that's the same point that's on both pieces, which, like I said, means that these pieces actually connect up to each other at 0. So if these don't come out to be the same, like you would, you got a 1 here, but let's say we got a 4 here, that means the pieces are not going to connect up, and you would have a discontinuity, okay? Now, if this is the only place that I've got to check is x equals 0, and they connect up, then that means this one doesn't have any discontinuities at all. So you could just say that this is continuous on entire number line. I guess I should say real number line. Continuous on entire real number line, which we're not writing things in interval notation, but like if you did interval notation, we're going to do that in a minute, that would be the same thing as negative infinity to positive infinity. Okay, next one is just y equals sine x. Of course, you should be familiar with what your sine graph looks like. Actually starting here and stopping here, like this portion of what you're seeing from here to here, that's actually the part that I would have had you to have memorized or learned when we were doing trig back in the earlier courses, in which that's the one cycle or the one period, that we used and did all the graphing with. Okay, remember, sine graph and actually also your cosine graph. Remember, it just goes hill, valley, hill, valley, hill, valley. It goes up to 1, down to -1, up to 1, negative, down to -1. And it just keeps doing the same thing from the left and to the right forever. So I mean, if you imagine this goes up and it comes down, goes up, goes down, goes up, goes down. There are no jumps, gaps, holes, or anything when you're dealing with your cosine graph or your sine graph, okay? So this one would be continuous.